Now we're going to go ahead and look at this definite integral, which means that we're really looking for the area between 1 and 5 underneath that curve. So it's that shaded area. We are going to find that area using infinitely many rectangles. Now I didn't draw infinitely many here, but we're going to use infinitely many rectangles, and we're going to be focusing on that ith rectangle. The definition of the integral looks like this. So the integral from a to b of f of x dx is equal to, it's a limit. So the limit as n goes to infinity. This is what gives us our infinitely many rectangles. And we are going to sum up the areas of those rectangles. So I goes from 1 to n. I counts our rectangles, and then we want the area, which is going to be a width times a height. Our height is the function value f of x, but that's going to be at f of x sub I, and I'm going to put a little star there for a sample point, and then delta x. So as I put this in terms of our ith rectangle, so this is our ith rectangle, we're going to be looking at right-hand endpoints. So x sub I lives right here. Now that height, so this is really, let me grab another color pen. This is really height times width. So the height of that rectangle is going to get me up to that function. So this is going to be f of x sub I. And then the width, I know that I'm at x sub I there, that width is right here, which is going to be delta x. And that width is fixed for all of our rectangles. Let's go ahead and put some of these into a little more specific language. So specifically, let's do a formula for delta x. So to get delta x, I've got to take my entire interval width, and this entire interval is going to run from a to b. So that's going to be b minus a, that's the interval width, and I'm going to divide that up into n rectangles. So I'm going to divide that into n rectangles. For our particular problem, a is equal to 1 and b is equal to 5. So for our problem, delta x is equal to 5 minus 1 divided by n, which is equal to 4 over n. I'm going to put a box around that so we can come back to that value. So we've taken care of delta x. We also need to figure out what f of x sub I is. Let's go ahead and start with that x sub I star. Now that sample x is going to give us a right-hand endpoint, which is going to put me right here. So that means, let me go back to my red pen. So that means that for x sub I star, I need to start where my interval starts at a, and then I'm going to be adding multiples of the width, multiples of delta x. So it's going to be a plus I delta x. In terms of our particular problem, x sub I star is equal to a, but in our case, a is equal to 1. So 1 plus I delta x, but delta x is 4 over n. And we can call that just a little more simply, x sub I star is equal to 1 plus, let's call that 4i over n. And that gives us our x sub I star. Okay, so now we've got this guy in the middle. Next, we need f of x sub I star. Lots of different notation that goes along with this, but if you take it step by step, piece by piece, you're going to get it. So next we want f of x sub I star. Okay, we know that f of x is x squared plus 3x plus 2. So it's going to be our x squared plus 3 times our x. Our x is our x sub I star plus a 2. So I'm going to go ahead and take this value and put it in for x. So 1 plus 4i over n, 1 plus 4i over n. And now I'm ready to tackle that definition. Now the definition is the limit as n goes to infinity, so that's infinitely many rectangles. I counts my rectangle, so I is going to go from 1 to n for n rectangles. F of x sub I star, that's my rectangle height, times my rectangle width, which is delta x. As we work with this definition, we're going to be focusing on just the summation to start. So I'm going to ignore that limit, and I really want to put in my delta x and my f of x sub I. I'm going to put both of those into that summation. So let's go ahead and do that work so that we can start to get to that answer. So I'm working on that summation. So I goes from 1 to n. Let's go ahead and put in f of x sub I first. I'm going to put that in parentheses. So that is 1 plus 4i over n quantity squared plus 3 times 1 plus 4i over n plus 2. And then we're going to go ahead and put in delta x. So delta x is next, and delta x is 4 over n. So let's get that in here as well. So 4 over n. 4 over n. I'm going to start by simplifying what I've got in my parentheses. I'm going to simplify that x of I first, and then we'll multiply through the 4 over n. But our goal is to isolate summations of I squared, I, and a constant, or 1. We're going to need these formulas, which is going to simplify our life a ton. So I've got some algebra, and then I'm going to be able to apply those formulas and then the limit. So simplifying what we can, I equals 1 to n. Let's go ahead and work first on the f of x sub I. Let's first work on what we've got in green there. I want to start by multiplying this out. It's a binomial squared. So I can use the formula a plus b squared is equal to a squared plus 2ab plus b squared. A is 1 here, and B is 4i over n. So as I multiply that through, I end up with 1 squared plus 2 times 1 times 4i over n. So that's going to be plus 8i over n plus that last term squared. So that's going to give me 16 I squared over n squared. Next, I need to multiply that 3 through, and I get plus 3 times 1, and then plus 3 times 4i over n. That's going to be plus 12i over n, and then the 2 on the end, so plus 2. And then on the end there, I still have that 4 over n. Let's go ahead and collect some like terms here. So in our summation, in the set of parentheses, my like terms, I'm going to do the I squared terms first, which is going to be this one. So I've got 16 I squared over n squared. And then I also want my I terms. So I've got an 8i over n and a 12i over n. That's going to be 20 I over n. And then finally, my constants. So my constants are a 1 plus a 3 plus a 2. That's going to be a 6. So plus 6. And then I've got the 4 over n. All I've got left to do before I start to apply those formulas is to distribute the 4 over n through. So let's take that 4 over n and distribute that one. So my summation, I'm going to do 4 over n times 16i over n squared. So that's going to give me 64. 64i squared over n cubed. Plus, now I'm going to multiply it by the 20i over n. So that's going to give me 80. So 80i over n squared. And then finally, 4 over n times 6. So that's going to be 24 over n. Now I'm adding all of these up. So I really want to add up each term separately. So it's like I'm distributing that summation through. And as I'm distributing that summation through, I can actually get rid of my parentheses now. Do you see how I did that? I can go ahead and take anything that doesn't depend on I, and I can factor it out in front. Okay, so here's what that looks like. So I end up with 64 over n cubed times the sum. I'm going to put in those indexes again. So this is I goes from 1 to n of I squared. Remember, that's one of my formulas. So this is exactly what I want. In the next summation, it's the 80 over n squared that can be factored out in front. So I get plus 80 over n squared. And then the sum I goes from 1 to n of I. There's another formula. And in that last one, if I put in times 1 as a placeholder, I can go ahead and take that 24 over n and factor it out in front of my summation. So I get plus 24 over n. The sum as I goes from 1 to n of 1. Each of the summations now have isolated the sum of the I squared, and the sum of 1. Let's go ahead and put those formulas in, and I'm going to try and write smaller. So this is going to be 64 over n cubed, and the sum as I goes from 1 to n of I squared is n plus 1, 2n plus 1, all divided by 6. Okay, that is the sum. So that replaces that first summation, plus 80 over n squared. The second sum can be replaced with its formula, which is n plus 1, all over 2. Okay, so I'm going to put a box around that so that you can see that this is my summation formula. That's that one. And then finally, the plus 24 over n. I'm adding that one n times. So that one turns out to be an n, and that replaces the last summation. Let's go ahead and simplify what we can simplify and then get to that limit. Okay, so what can we cancel here? I can definitely cancel a single n. I can cancel this n, and I'm left with n squared here. I can cancel a 2 out of the 64 and the 6. So 2 into 64 is 32. 2 into 6 goes 3 times. Okay, now let's look at the next term. 2 goes into 80 40 times, and I can cancel one n, and it leaves me with a single n there. And in the last one, I can cancel those n's completely. So what I've got left is, let me move this up again. I've got 32 over 3n squared. And inside, I've got this product that I need to multiply out. So let's go ahead and multiply that product out using FOIL. 2n times n is going to be 2n squared. Outer is n, inner is 2n, so I get plus 3n. Outer is plus 1. Okay, moving on to the next one. I can go ahead and take that 40 over n and multiply it by n and multiply it by 1. So I end up with plus 40 over n times n. Those are going to cancel. Yay, cancel, cancel. Plus 40 over n times 1. That's 40 over n. And then that last term is going to be 24. Okay, over here to this first term, I need to distribute that 32 over 3n squared through. Then I'm ready for the limit. Then we're done. Oh my gosh, this is such a long process, but we are almost there. Okay, so I'm going to take that 32 over 3n squared. Let's multiply this through. So we get 64. 64n squared over 3n squared. Those n squareds cancel. And distributing it times the 3n, I get plus. Let's see, that's going to be 96. So 96n over 3n squared. And then multiplying it by 1, that's the easiest one, I end up with plus 32 over 3n squared. Okay, then I've got plus 40. Let's combine these, 40 and 24. So plus 64 plus 40 over n. I'm going to take a shortcut because, oh my gosh, this is a lot of writing. So I'm going to go ahead and just erase the equal sign out in front, and let's go ahead and put in the limit. This was the last part of the equation for the integral. So I need to apply the limit as n goes to infinity for all of these. Well, remember that the limit as n goes to infinity, of 1 over n is equal to 0. So we're going to be using that fact quite a bit as we run through these. So as I run through each of these, let's go ahead and start with that first one. The limit as n goes to infinity of 64 over 3. That's just 64 over 3. There's no n there. In the next one, I can cancel an n, and I'm left with an n to the first in the denominator. I have an n in the denominator. So 96 over 3n as n goes to infinity. This guy goes to 0. Same is true of the next term, right? 1 over n goes to 0, so 1 over n squared certainly goes to 0 as well. I've got that 64, so plus 64, and then on the end there, n goes to infinity, so 40 over n also goes to 0. As a decimal, we can say that this is about 85.333, so 0.333, or we can say that this is 256 divided by 3. And when we say that this answer is 256 over 3, we mean that the value of this integral, or that area under the curve between 1 and 5, is 256 over 3. You are doing so great. Take a look at this next video.